All right, let's talk about what separates a good AI practitioner from a truly great one. The kind of person who doesn't just use AI, but builds the systems that power it. Today, we are diving deep into a curriculum that's designed to do exactly that, to turn you from a practitioner into an architect. And believe me, this isn't some quick reading list. We're talking about a serious university level roadmap for mastering modern AI, right from the very foundations. So let's jump right in. Okay, let's kick things off with a question that probably hits close to home for a lot of us in tech. Why is it that some of the smartest, most capable candidates, people who know all the latest libraries, who have impressive projects on their GitHub, why do they sometimes completely bomb those advanced technical interviews? It's like they hit a wall. What's going on there? What's the piece they're missing?
And here it is. This is the diagnosis. It turns out the problem isn't about knowing PyTorch versus TensorFlow or any specific library for that matter. No, the real breakdown happens way, way deeper. It's a weak foundation in the core fundamental theory that everything else is built on.
This really boils down to two very different paths you can take in your career. On one side, you've got the API consumer. They're great at using the tools that exist today. They follow the trends, they implement solutions. But on the other side, you have the system architect. This person builds the tools. They reason from first principles. They don't just implement solutions, they design totally new systems. This curriculum we're talking about, it's the bridge to get you from that first column to the second.
So, how do you actually make that leap? Well, it all starts with a change in philosophy. It's about thinking from first principles. What does that philosophy look like in practice? Well, first, it's a properly structured university-level framework. We're talking real academic rigor here. But, and this is key, it's blended with what actually works in the industry. It's the complete opposite of those superficial bootcamp approaches that just teach you the latest hot library. The whole point is intellectual durability. We want to give you knowledge that's going to stick around, stuff that will be just as valuable 5, 10 years from now. You could almost call it the anti-bootcamp.
All right, let's get into the first phase, building the foundation. And I mean the absolute bedrock, the stuff that's totally non-negotiable for modern AI, math, and high-performance computing. Seriously, you can't build a skyscraper on a shaky foundation, and you sure as heck can't build a large language model without this stuff. And I absolutely love this way of framing it. This is why we have to start with linear algebra. Forget thinking about it as just solving for x and y. No, think of it as the physics of the universe where neural networks live. Every single weight matrix, every activation vector, every gradient, it's all just an object existing in some crazy high-dimensional vector space. If you don't understand the physics, the geometry of that space, you're flying blind. And check this out. This table makes that connection between theory and practice so incredibly clear. Look at linear algebra. You don't get the eigenvalue spectrum? Well, good luck explaining why your gradients are exploding and your network training is totally unstable. Or how about probability? You mix up posterior and prior probabilities, your whole grasp of how generative models work is just fundamentally broken. You see the pattern here? Each one of these boring math concepts maps directly to a huge AI application, and a very common way people fail interviews.
Okay, so let's talk tools. In AI, we have what's often called the two-language problem, and this analogy is perfect. Think of Python as the steering wheel. It's easy to use, it gives you high-level control, you tell the system where to go. But C++, that's the engine. That's where the raw, high-performance computation happens. If you want to be a real system architect, you can't just know how to drive the car. You've got to know how to build and tune the engine, too.
And this isn't just about reading books. A really crucial project in this curriculum is to get your hands dirty. You're going to implement your own custom matrix multiplication, the core of deep learning, in C++. Then you'll wrap it so you can call it from Python. This one project is so powerful because it forces you to bridge that gap between the easy-to-use steering wheel and the high-performance engine. It makes you confront the real bottlenecks in AI head-on.
Okay, foundations built, now it's time to level up and start mastering the modern canon. This is where we trace the story of machine learning, from its classical roots all the way up to the wild world of generative AI we're living in today.
And this timeline here is so important to understanding how we got here. We look back at things like RNNs and LSTMs, not just to learn how they worked, but to really understand why they broke. See, their biggest problem was that they had to process things one by one by one. It was a massive bottleneck. You couldn't parallelize it. Then came the attention mechanism. It completely shattered that bottleneck by letting the model look at all parts of a sequence at once. And that single idea opened the door for the transformer, which has basically become the general-purpose computer for this entire AI revolution.
So right at the heart of every transformer is this formula. Now, it looks a little scary, I know, but the core idea is actually pretty elegant. The Q, K, and V stand for query, key, and value. And this whole equation is just a super clever, efficient way for the model to calculate how much every word in a sentence should pay attention to every other word. And guess what it's all built on? Yep, the exact same matrix multiplications and vector spaces from our linear algebra foundation. See how it all connects?
Okay, so we've got these incredible, massive models. But there's a problem. How on earth can anyone but a handful of giant companies afford to actually train or fine-tune them? Well, that brings us to this number, 10,000x. This represents a massive leap in efficiency thanks to a bunch of techniques we call PEFT, or parameter efficient fine-tuning.
The most famous of these techniques is called LoRa, and the idea behind it is just, it's pure genius, and it ties right back to our linear algebra foundations. So instead of trying to update the entire massive weight matrix of a model, we're talking billions of parameters. You freeze it, you don't touch it. Instead, you train two tiny, tiny little matrices on the side, and you just add their product back to the original. You're updating what's called a low-rank approximation, and it is thousands of times more efficient. It's an incredible hack.
All right, we're at the final stage of the curriculum. You've got the theory down, you understand the models inside and out, but here's the final test. Can you actually make this stuff work in the messy, complicated real world? This is all about engineering the reality, MLOps and system design.
And here is a major wake-up call for anyone getting into this field. That cool model code you wrote in your Jupyter notebook, that's about 5% of the actual work. Just 5%. The other 95%, that's the MLOps and infrastructure. It's the data pipelines, the deployment, the monitoring, the logging, all the unglamorous but absolutely critical stuff that actually turns a cool science project into a reliable product that people can use.
So how do you train these monster models that are way too big to fit on a single GPU? Well, you have to distribute the work. Think of it this way. The old way, DDP, is like trying to build a giant Lego castle by giving every single builder a complete copy of the entire castle. It's super redundant and wastes a ton of memory. The newer, smarter way, FSDP, is different. It's like a master builder who only gives each person the specific Lego bricks they need for their one little section. There's zero redundancy. It's way, way more efficient, and it's how we train today's biggest models.
So you go through all of this, the math, the HPC, the models, the systems. Where does that leave you? It leaves you right here, ready to architect the future. This is what gives you a real, lasting competitive advantage.
And this quote really brings the entire philosophy home. The technologies of 2026, transformers, diffusion models, and LoRa, are not magic. They are transient, highly optimized implementations of eternal mathematical truths. I mean, think about that. All the cool stuff we're talking about today, it's not magic. It's just the current, fashionable application of deep, timeless principles. If you master the principles, you'll be ready for whatever comes next long after these specific technologies are obsolete.
Now, let's be real. This isn't something you're going to knock out in a weekend boot camp. This whole curriculum is laid out as an intensive 18 to 24-month journey. It's a serious commitment. But the goal isn't just another certificate for your LinkedIn. It's a deep, durable expertise that will last your entire career.
And that brings us right back to the beginning. Taking on a path like this is about making a choice. It's the choice to move beyond just using the tools everyone else is using and into the realm of designing and building the next generation of intelligence systems. So the only real question left is, are you ready to architect the future?